All right, so we're going to look at what's called integration by substitution. So just like when you develop the idea and some strategies for taking the derivatives of things, you're going to need some strategies for taking the integrals of some more complicated functions. So some prior knowledge we need for this is we need to understand what the chain rule is. And that's how we're going to start things. So we're going to start by taking the derivative of a composition of functions. So let's jump into it and see how we go. So let's consider this function, 2x squared plus 1, all to the power of 5. You can sort of see that it's composed of two functions. The inner function, which is 2x squared plus 1, and then you can sort of think of it as all being raised to the power of 5, which you can sort of think of as an outer function. So if we were to take the derivative of that, that shouldn't hopefully be too tricky, given you're learning about integration by substitution, because we're just going to apply the chain rule. So we're going to say that u equals 2x squared plus 1, and du dx, the derivative of u with respect to x, is 4x. Okay, you're going to say then that y equals u to the power of 5. Okay, so y, we can think of it as like sort of this outer function. You're taking the inner function, which is u, and raising it to the power of 5. And so dy du is 5u to the power of 4. We've taken the derivative of y with respect to u. Okay, and then by the chain rule, which we have here in blue, it says that the dy dx is going to be dy du multiplied by du dx. So you're going to multiply these two things together. So doing that, you're going to get the following. You're going to get dy dx equals 4x multiplied by 5u, which is 2x squared plus 1, all to the power of 4. Okay, and then you can just simplify this part out the front, can't we? So we can just say 4x times 5 is 20x. So yeah, we get dy dx equals 20x multiplied by 2x squared plus 1, all to the power of 4. All right, we're going to come back to this in a moment once we talk about the theory behind integration by substitution, because ideally what we should be able to do is we should be able to integrate this, which with the skills we have up to this point would be very challenging. But what we're going to learn is how to do that, and then it would get us back to this being the answer, right? So let's talk about integration by substitution. So let's imagine to begin with that we've got some function y, and that's equal to the integral of a composition of functions. Okay, up to this point, we don't really have a chain rule, shall we say, for integration. So this would be challenging. And this is why we need to develop this idea of integration by substitution. So what we do is we let g of x equal u. So we let the inner function, and we call that u. So just rewriting that line where g of x equals u, we get y equals the integral of f of u, but now we're integrating everything with respect to u. Okay, we've sort of got f as this sort of outer function, g of x is this inner function, we've called that u. So now we're integrating everything with respect to u. There's no x's left in this, right? Okay. If we take the derivative of both sides, well, the derivative of y is with respect to u, I should say. The derivative of y with respect to u is dy du, and the derivative of this right-hand side with respect to u is just going to be f of u. If we think about that for a moment, this is the integral of f of u du. Derivatives and integrals are opposite operations, or derivatives and antiderivatives are opposite operations. So if you take the derivative of this side, you're just left with f of u. Okay, this is where it gets a bit tricky from here. This is where we need to look at the chain rule now. So we just take our chain rule, which is over here, and we say, all right, dy dx then is equal to f of u. So f of u is dy du. So that's what I've just replaced this dy du with f of u from this line here, multiplied by du dx, because that's du dx over here. Okay, and so what we get is this. What we're going to do from this step to this step is we're going to take the integral of both sides. Take the integral of dy dx. You just get y. So we're taking the integral of both sides with respect to x. So you get y on the left-hand side, and you get the integral of f of u multiplied by du dx dx. Okay, so to go from here to here, we take the integral of both sides. And so you probably think to yourself, why is this an interesting conclusion? Well, let's look. The kinds of questions you're going to be asked are going to require you to exploit this property of integrals. So let's have a look at an example, which is this example. Imagine we needed to find the antiderivative of this. So 20x multiplied by 2x squared plus 1 all to the 4. Okay, so we're trying to find the antiderivative of that. So our answer should be this, right? Because we differentiated this to get to here. So if we anti-differentiate this, we should get back to here. Okay, so what we're going to do is we're going to make a substitution. So we're going to say u is 2x squared plus 1. So that's that sort of inner function. And so du dx is 4x. Take the derivative of this with respect to x gives you 4x. Okay, so what you get is this. You get the integral of 20x. That hasn't changed. This thing here is just going to be u to the power of 4 dx. Okay, and now we need to exploit this information here. So I'm just going to express 20x as 4x multiplied by 5 u to the 4 dx. Because now what you might start to notice is 4x is du dx, so that's this part of it. F of u is 5u to the 4. Okay, so then what we get is 5u to the 4 multiplied by 4x. I haven't really changed this line, but I've just written it a little bit differently. And we've said, all right, du equals 4x multiplied by dx. If we just multiply dx to both sides, remember we're allowed to do that because dx sort of represents the width of an infinitely small rectangles. So we can multiply both sides here by dx. So we get du equals 4x times dx. So this part here, 4x dx, is just du. So now we're integrating this thing, 5u to the 4 du, because 4x dx is du. Okay, so, and we know how to integrate something like this. Now we can just apply what we've learned about integrals previously. You bring the power down, so it's 1 over 4 plus 1, so that's 5. So 5 over 5, u to the 5, which is 1 u to the 5, and don't forget the constant of integration. And finally, after all that, we sub in u back in. So you get 2x squared plus 1 to the 5 plus c. All right, don't forget the constant of integration. So yeah, this is a good example of how you would use u substitution to find the integral of something. So hopefully find that helpful, and you just need to go out and practice them. It should generally be pretty obvious what the inner function is when you're being asked to integrate something. So let's have a look at a problem so you can practice things. So see if you can find an antiderivative of 3x multiplied by e to the x squared by making an appropriate substitution. And again, I've just shown you the graph. I thought this would be a little bit more interesting, to be honest. I thought 3x multiplied by e to the x squared would look a little bit cooler, but it is what it is. And again, you don't need the graph to find an antiderivative of this. All right, let me know how you go. That's probably quite a challenging idea. Yeah, good luck with all your studies.